Hello again. We're still in heat lost versus heat gained, but this one's equals heat gain, sorry. But this one is a little bit different in that there's no chemical reaction happening. What happens here is they take 50 grams of hot water and they pour it into the same container as 50 grams of cold water. And they ask what's the final temperature of the mixture. Now, if you're really keen, you might think something like it's going to end up at a temperature that's halfway between the 5 and the 80. In this question, that would be right, but only because there's equal amounts of the two types of water. Obviously, if you put one drop of 0-degree water in a 100-degree ocean, you're not going to land on 50 degrees. The temperature change depends on how much of each type of water there is. But in this question, because it's 50-50, we are going to end up right in the middle. And if you notice that, good for you. But let's do this algebraically the way we're supposed to, because then we can give you uglier numbers and you'll be able to handle it. So if we break this up like any other heat lost equals heat gain problem, there are two things happening. We have hot water cooling down, and on the other side we have cold water heating up. Cold water, I'll say warming because that's one word, it's quicker to write. So the hot water is going to give up some energy, the cold water is going to absorb some energy, and that'll keep happening until they end up as one big mass of water that's all at the same temperature. Because they're both temperature changes, the energy involved is going to be mc delta T, and so will this one. No chemical reactions, so we get a break from N delta H. Now, what makes this one ugly is at the moment we can't calculate either one of these sides. Over here we know the mass and the specific heat, and we don't have the temperature change. On this side, exact same situation, so we're going to need algebra to dig our way out of this, and we're also going to have to think about delta T in a little more detail than we normally do. For this question, we have hot water that starts out at 80 degrees, and we have cold water that starts out at 5 degrees. When you pour them together, you're going to get kind of medium temperature water in the middle. It's going to be some temperature that's lower than 80, higher than 5. We don't know what it is. I'm going to use TF for it. Final temperature, the temperature that we end up at when we're done. And instead of delta T, we're going to have to write some algebraic stuff using this TF. So this will be a little more mathy than you're used to, but we will get through it. For the hot water, the mass is 50 grams. The specific heat, it's water, 4.19. The temperature change is going to be from 80 degrees down to whatever this final temperature is. I don't know the final temperature, but I can still write that the temperature change is 80 minus TF. I can do the same thing on the cold water side. Mass here is 50 grams. Specific heat, cold water is water, so 4.19. The temperature change here is from 5 degrees up to TF, which we can write TF minus 5. Now, I just kind of quietly cheated something here, and wondering if you noticed it. Do you see something that I was a little inconsistent about between these two? Over here, I put the TF second, and over here I put the TF first, basically. What's going on with that? Well, I want both delta T's to come out positive. And so to arrange that, I always went higher temperature minus lower temperature. So here, 80 minus TF because I knew the TF is going to be like 40 or 50 degrees. It's going to be lower than 80, so this number will come out as a plus. And 40 or 50 minus 5 will also come out as a plus. I just arranged them that way because when we write an equation here, it'll be difficult to solve if I have a positive side and a negative side. You can't really have positive number equals negative number. So to make my math work, I need to have both of these coming out positive. And I'm putting an equals between them because just like all the other problems we've done, one side's giving up energy, and that exact same energy, the same amount, is getting absorbed on the other side. So I know these amounts have to match. And now we're going to beat this with the math stick until it gives us an answer. There's a really nice way we can simplify this. Do you see it? The really hard working way here would be to go 50 times 4.19, which is 200 and, oh, what is it? 209.5 or something, and then distribute that through these brackets, but we can do something much simpler. We can divide both sides of this by 50, and the 50s just cancel out. And then we can divide both sides by 4.19, so those also cancel out. And so this equation goes from being a little bit awful to being not too bad. It's 80 minus TF equals TF minus 5. How do we solve that? Pretend you're in math class for a second. We're trying to solve for TF, which means we want to get all our TFs to one side of this, so let's get rid of the negative one because negatives make me sad. If we add TF to each side of this equation, these two cancel. Gone. Now we have 80 equals 2TF minus 5. Now that I have all my TFs on the right, I'd like to get them alone, so get rid of that 5, negative 5. The opposite of a negative 5 is a plus 5. These cancel. 2TF equals 85. Divide by 2. Final temperature is 42.5 degrees. In general, if the amounts of water are not the same, if these hadn't both been 50s, we couldn't have canceled them out. If these were different materials, if you poured like benzene into alcohol or something, then you'd have different specific heats too. Then none of this stuff would cancel out, and you'd get a really yucky equation here with a lot of decimals in it. But the overall idea would still be the same. Get all your TFs to one side, get all your numbers to the other side, and just do algebra to it until you get your solution. This one was easy. The next one will be worse. See you there.